to Electronics Bit by Bit. This is a continuation of Project 3 where we'll be exploring all things combinational. Last week we went over the analysis procedure where we produce Boolean functions and a truth table when given a particular circuit. This week we'll be designing a circuit that meets the specification criteria of a particular problem statement. So our problem statement is we need to create a converter that takes BCD code values and turns them into XS3 code values. First, we need to understand what's being asked of us. So first we need to establish what is binary code. Binary code is used to represent numbers, text, and computer operations using a two-symbol system. Those two symbols are 1 and 0, and this is the main language of digital technologies. Now, an n-bit binary code is a group of n bits that produces up to 2 to the power of n distinct combinations. For example, to represent 4 unique elements, you would need 2 bits, with each element assigned to one of the following combinations: 0, 0, 0, 1, 1, 0, and 1, 1. When we look at the decimal digits, which are in base 10, we would require 10 unique elements. Therefore, the smallest bit binary code we could use is a 4-bit code. When the number of elements in a set isn't a multiple power of 2, there is going to be unused bit combinations, as is the case with decimal digits. So we use the first 10 bits to represent a binary number and leave the last 6 unassigned. Now, different binary codes can be obtained by arranging 4 bits into 10 distinct combinations. Even though the binary number system is most commonly used in computers, most people are used to the decimal system. On top of that, operations like addition and multiplication need to be done to convert binary numbers to decimal numbers and vice versa. We can see here we're trying to convert 185 in base 10 to binary code, and we're having to divide the quotient by 2 over and over and keep the remainder fraction until the quotient becomes 0. Now, this is a lot of work, and there's something that could make it easier, which is something called binary coded decimal, or BCD. Now, binary coded decimal is a system of writing numbers by assigning a 4-digit binary code to each digit 0 through 9 in a decimal base 10 number. Each digit is encoded separately, and the full number is first segregated into its individual digits, and then these digits are represented by their equivalent 4-bit binary coded decimal codes. As we can see here, to convert 185 to base 10, in base 10 to BCD code, we separate it into 1, 8, and 5, and then we convert 1, 8, and 5 into their BCD digits. Now, another example of this is XS3 code, which is a coding system that's used in some older computers. XS3 codes can be obtained by adding 3 to the decimal digit and then expressing it as a 4-bit binary number for each digit. Now that we have an understanding of what's being asked of us, we can get back to the design procedure. So step 1 is determining the inputs and outputs, and we've established that any binary codes for decimal digits will require a minimum of 4 bits. This means that the BCD inputs will require 4 bits, and the XS3 outputs will also require 4 bits. Step 2 is deriving the truth table. Now, a binary code will have some unassigned bit combinations if the number of elements in the set is not a multiple power of 2. So we're using a binary code that distinguishes among 10 elements, and so we have to have at least 4 bits, and 6 out of the 16 combinations will have to be considered inputs whose values we don't care about. So we will set their output to be X. However, when using K-maps, you can designate those don't care values to be either 1 or 0 if it makes simplifying the circuit easier. So our inputs are just going to be the BCD code, and our outputs are going to be the BCD input plus 3 in binary. Step 3 is finding the Boolean functions and simplifying them. So since we have 4 output variables, we're going to have 4 output functions, w, x, y, and z. So then we use K-maps to simplify each of them, and you can see this is making use of the don't care values, which is making it easier to simplify the functions. So then we produce the circuit and verify if it works. We do that by entering each of the valid inputs into the circuit to see if it gives us the output we're looking for. As you can see here, I further simplified these functions. If you want to know how I did that, there's a link below to the article that's with this video. So that's all for designing circuits, and next week we're going to be building adders, which I'm very excited about. Thanks for listening. I'll see you next week.